So here we go. Calc 1, Day 1. All right, so the first thing we're going to talk about are tangents and velocity problems. And so a couple of important words that you're going to need to know that we're going to talk about quite a bit is a secant. Don't worry about the definition. I'll get to a secant and demonstrate it for you guys so you can see it, but you can read it if you'd like. And then the other thing that we're going to talk about is also the tangent. And so I'm going to demonstrate those for you guys so that you guys can best understand them by showing you what happens. Okay? So let's do this. So I'm going to use an example of a problem that I love, and I'm probably going to use it a zillion times during our class. So you're going to get sick of this problem. So the problem that I'm going to use is f of x is equal to x squared. It's a simple problem that we all know, but what it will do for us is it's going to allow us to demonstrate a few of these things. So just plotting some points real quick so that we can have this. I wonder if I want to be more. That's 1, 2, and 4. So 1, 2, 3, 4. Okay, so what I've done here is I'm going by half increments, just because I want my picture to be a little bit bigger for you guys, okay? Okay, so I want these kind of bold points here. Okay, so, excuse my son. So the first thing that we're going to talk about is the secant. And so with the secant, what ends up happening is it says that the secant, if Q is any point on the curve different from P, then the line through P and Q is the secant line. So something important. I'm going to call this point right here my P. Okay? So this point here at 2, 4 is going to be my point P. Okay? So that's where I'm going to try to find, I'm going to lead to trying to find a tangent. Okay? So the first Q that I'm going to use, this as my Q1. So my first Q1 is going to be negative 2, 4. Okay? And what we're trying to do, and this is where the problem lies in calculus. I'll use red for this. If I had a slope that was going through this point, let's see if I can get it to go straight through. That's only going through one point. It's going through that point specific P, right? So that's called the tangent line. That red line is the tangent line, and the reason it's called a tangent line is a tangent touches a curve at one specific point, right? But the problem in calculus is if it only touches this thing at one point, how are we able to find the slope? Does that make sense? We can't find the slope if we have only one point, because what ends up happening is our denominator ends up being 0, and that gives us something that's undefined. So in order to work around that, two gentlemen worked on this, right? A guy named Leibniz, who we use all of his notation, and then a guy that you guys know a little bit better and hear his name quite a bit more, a gentleman by the name of Sir Isaac Newton, right? It's interesting that Newton gets so much credit for people for calculus, and yet we use Leibniz notation for everything that we do. But That's those two guys. Now, going back to a secant. So if I use Q1 and the Q1 was that negative 2, 4, my tangent line, isn't my tangent line going to be horizontal? I'm sorry, not my tangent line. My secant line is going to be horizontal, right? And if my secant line there is horizontal, what's the slope of that dotted line? What do you guys think it is? Yeah, it's 0. So the slope ends up being 0, right? We have a 0 slope. And so is that purple dotted line a good representation of that red line? Nope, not at all. In fact, it's terrible, right? So what we need to do then at that point is choose a different Q. So we're going to use a different Q, and so I'm going to use a different color, and I'm going to now use this guy as my Q. So this would be negative 1, 1, and if I use that guy, I end up with this, right? Is that a good representation? Clearly not. But is it a better representation than Q1? Yeah, it's getting better. So notice something that's happening as we're moving. We're moving to the right, closer and closer to our P point, correct? So our Q is shifting to the right. The X value is moving to the right to get closer and closer to P. Let me do one more. And Q3 is even better than Q2, right? Well, what we're going to do to eventually lead to getting the tangent is that we're going to do so many Qs that we're going to try to get as close as possible to P without actually getting to P. Does that make sense? So if that point is 2, 4, I may want a Q that's 1.9, comma 3.81. And then that would be a very good approximation of what that red line is. Does that make sense? And even better than 1.9 would be 1.99. And better than that, 1.99. And then better than that, 1.99. And, you know, infinite 99999s. The one thing that happens here is we never get to 2, 4. So we never get our X value to become 2. Because if it becomes 2, we end up with something that's undefined and it doesn't work. Does that make sense? So this is the introduction to the limit. So what ends up happening here is, here's some notation for you guys to see. So what we did to find the secant, we'll go M secant, was we took points and then found the slopes, right? So if I did it for Q3, that's at 0, 0. I'd have gone 4 minus 0 over 2 minus 0 would give me a slope of 2 for the secant from Q3 to P, right? And the slope, so this was for Q3 to P. If I did the secant from Q1 to P, wasn't that 4 minus 4 over 2 minus a negative 2, which would give me 0 over 4, which is 0, right? So we notice we're getting, as we're moving, we have different slopes. But something important that comes into play is, if we use our function, we'll go the limit as we approach 2, as x goes to 2. So what's happening here is my q1 is over here for x, then it shifts over here, then it shifts here, then it shifts here, and we're trying to get closer and closer to this x value of 2. So what this is saying is, as we're coming from the left, we're going to 2. Now, in fact, it's telling us as we're coming from both sides, because there's no distinction of direction. As we're coming this way, we're approaching 2, and as we're coming this way, we're approaching 2. We'll delve into that in just a second. But then, how do we find slope? Isn't slope the y value subtracted minus the x value subtracted? Right? So what I'm going to do is I'm going to use the function. So I'm going to say, okay, the function was x squared at some specific value. That specific value is 4 for y, right? Because it's 2 comma 4. Over the denominator, oop, that should be a y. Oh no, x squared, that's the function, that's right. And then the bottom is going to be x minus 2, right? Where this here is just a representation of these points 2, 4. Are we okay with that? Any questions so far? It's okay. This is actually a little bit deep. Quite an introduction to the class, right? And then from here, what we end up seeing is this is something that will be factorable. And so we'd have the limit as x approaches 2. The top is a difference of squares. So don't we get x minus 2 over x plus 2 over x minus 2? Right? So then that's going to give me the limit as x approaches 2 of x plus 2. And then from here what we can do is something called a direct substitution, which is 2 plus 2, which tells me that the slope of that red line is 4. So once we have this here, that's the slope of the tangent. It's no longer the slope of the secant, it's the slope of that specific line. Now, I'll talk about this a lot in this class. When I talk about finding tangents, you're getting to the neighborhood, you're never getting to the house. So what it means is I'm getting super, super, super close to, in this case, the number 2, but I'm never actually getting to the number 2. Does that make sense? If it doesn't make sense, I can explain it another way. We're okay?
Yes.
Okay. Now, using that example that I just did, can you guys do this one? I'm giving you the function, I'm giving you a p, I'm giving you what the q could potentially be. Can you guys find for me the tangent of this guy? I'll put it so you guys can see. So I'll give you a little bit of guidance. What are we approaching? What number are we approaching? Right, so if I'm going to go, okay, it's the limit as x approaches what number?
3.
It's approaching 3. Perfect. Now, it's going to be the function, the y value. So the y value in q is what? It's the x squared minus the y value of the p, which is our 9. And then in the denominator, it's the x of q minus the x in p. We okay? Okay. Now, from here we know we can factor, and we end up seeing that the limit as x approaches 3 of x minus 3 times x plus 3 all over x minus 3 is going to give me the limit as x approaches 3 of x plus 3, which will give me 6. So what I end up finding out in this problem is that the slope at 3 ends up being 6. The slope at 2 ended up being 4. Can you guys take a guess what the slope would be at 4? But someone said it. It's 8. What we end up finding out in this problem is the tangent slope to x squared is always just twice the x value. Isn't that cool? Now, something cool that can happen is if I ask you for the tangent line for this problem, we can find that. So the tangent line of this guy ends up being, we know the slope now is 6, right? So we know the slope is 6. What's the point that we have? 3,9. Because we're trying to find it at that p, that's the point that we have to use. So it's 3,9. And so from here, what ends up happening? Did someone say something? We're okay? Okay. So then from here, what I'm going to use is I can use a point slope form. And I'll go y minus 9 is equal to 6 times x minus 3. And this, to me, is perfectly good enough. Now, one of the problems, unfortunately, is WebAssign gets picky. And since WebAssign is picky, they're going to want it in slope-intercept form. And so you'd go y minus 9 is equal to 6x minus 18. And you end up with 6x minus 9 as the answer that WebAssign will typically want. Okay? But what this ends up representing is the line that touches the y equals x squared curve at 3,9. Okay?
That's not.
What's that? I'm sorry?
That's not the tangent line? Or is it?
This is the tangent line. Yes, this is the tangent line. And the reason it's the tangent line is because of taking the limit. If we didn't take the limit, it would be a secant line. Does that make sense? Okay. Now, to point out some things for you that's important. So, velocity, and this is the whole point to what we're doing here. The whole point of this is to point out the distinction between secant and tangent in terms of physics. And so in terms of physics, the secant, what it does for you is it gives you an average rate of change. An average. Or what it does is it gives you average velocity. Okay? What the tangent's going to do for you is it's going to give you instantaneous rate of change or the instantaneous velocity of an object. So, if I wanted to know, like, at what speed a car hit a tree, I can do the math to find out at exactly the moment that the car touches the tree, how fast the car was going. And that's different than your speedometer would have. But that's the whole point to this. The distinction between secant and velocity, or secant and tangent, is average versus instantaneous. Okay? So when you have homework questions today and they ask for average rate of change, all you're going to do is take the slope. So in this case, the example that they're giving us this right here. The secant is going to be f of x1 minus f of x naught over x1 minus x naught. Or 2 points, just find the slopes. Okay? For the instantaneous, the distinction or the difference is you're going to take the limit as you go from x1 to x naught. So as you're going from your q to your p, you're going to take the limit like I did in my examples previous. Are we okay with that? If you're unsure, please speak up and I can clarify. So, just so you guys get an idea, so in this case, if I give you 2 points, right? I don't know. Let's say I gave you 2, 3, and 5, 7. To find the secant, we're just going to take the slope, right? So the secant of this thing would be, and let's call this P, and let's call this Q. All I would do here is I would go, okay, 7 minus 3 over 5 minus 2, and that's going to give me, what, 4 over 3? That would be the secant slope. That would be the average rate of change from P going to Q. From Q going to P. Okay? In this case, down here, using using that example, I would go the limit as x goes to 5 of whatever the function is. I don't know what the function is because I just made it up. Minus 7 over whatever the function's x value would be, minus 5. Does that make sense? Or do you want me to make a concrete example so you guys can actually see the x and y values? You want a concrete example?
Concrete example.
Okay, cool. I'll make one. That'll be better for you guys. I'm still too abstract. That's why I need you guys. Okay, so let's say I used f of x is x cubed, right? So if I used x cubed, let's say that I had 1, 1, and 3 and 27, right? So for this top example, and let's say this is the P that we're trying to go after. So in this example, I'm going to go, all right, 27 minus 1 over 3 minus 1. This ends up being my secant, right? So that's going to give me 26 over 2, which tells me that the slope from the average the average rate of change for this thing is 13, going from Q to P, right? In the tangent one, I'm going to take the limit as x goes to 3 of my function value. So my function is going to be x cubed minus 27 over x minus 3. Does that make sense? And in this case, this is factorable. And you guys totally know how to factor cubics, right? So it's going to be x minus 3, x squared plus 3x plus 9 over x minus 3. The x minus 3 cancel, and so the limit as x approaches 3 of x squared plus 3x plus 9 is 1827. So the instantaneous rate of change at 3 for a cubic function is 27. Does that help to make the distinction between a secant and a tangent? Yes?
My name is Daniel.
Yeah.
If you're asking for names.
Oh, yeah, cool.
So when it says like limit, so it's like an x approaching, so for the secant one, it was kind of just like the symbols kind of made it look like a little more like confusing than it was, but then like for a tangent, so if it's like as like limit like x.
So you're talking about these things?
Yeah.
Yeah, general notation?
Yeah, like honestly, like it's the same formula like for rate of change, I think.
Yeah, it's the same up as what I did earlier. I was just putting it in the general form for you.
Yeah, so like that part's like kind of good, but for like tangent, so like limit is like as x approaches 3, like so on the bottom, you would just always do like x minus whatever that number is.
Whatever the p value is. So in this case, this is my p. This is what I'm approaching. So the bottom's always going to be the function, right? The x part of the function minus the x value. The top is always going to be the y part of the function minus the y value. I think you're muted. Sorry. Daniel? I may have lost him right there. Okay. But are you guys okay with this?
Good question for the tangent. So the answer would be 27.
27, and then if I gave you units, so if I had said like meters per second, it would have been meters per second.
Okay.
Does that make sense? Or if I would have done feet per second, miles per hour, whatever the units are that I would have given you, that tangent one is a velocity specific at an instantaneous moment, where the secant is an average over time. Does that make sense?
Yes.
Okay.
Yeah, totally. And you plugged in 3 into those x's, like for x squared plus 3x.
Right here. Right?
Oh.
I plugged the 3 in right here. So 3 squared is 9, plus 3 times 3 is 9, plus 9, so 9 plus 9 plus 9 is 27. This is what I did right there, and I'll talk about that more as we're moving forward. It's called a direct substitution. As soon as I see that I won't get undefined, I can directly substitute in.
Okay.
That's just a simple way to do it. Yeah, no problem. Like I said, you guys asking the clarifying questions makes it that much better. So I appreciate you guys asking the questions. Daniel, I think it is your name, right? Who's asking the question?
The last question, that was someone else.
Yeah,
But
yeah.
About the tangent, then I think, my Zoom froze. So.
Okay, I was just making sure that you got everything that you needed answered.
Oh yeah, if I could actually go back to like just so like instantaneous rate of change, just like for limits, because I mean it's like a new concept, but I'm still kind of just trying to like grasp it.
Okay, no worries. So watch this. This may help. Okay. So if I have this is just the cubic, right? So I'm going to show you the difference between the tangent and the secant real quick pictorially. So
Did you just draw something on your screen, or are you like, is it paused? You guys can't tell if there's something.
So there should be a cubic function that I drew. Did you see it?
No, I think it's on my end.
Oh. Do the rest of you see it?
I do. I can see it.
Okay, thank you. There should be a picture of a cubic function.
Okay.
Okay, no problem. So just watch this, guys. So this is, I think I used 1, 1, right? Yeah. So this is Q1. Hopefully he gets back so I can show him. But this is the secant, right? It's basically what it's doing is instead of going along the function, it's trailblazing its own path. Does that make sense? So the slope of that is the average velocity from Q to my red dot P. This red line is what the tangent is. And you see it only touches the function at one point, where the Q drawing is touching at 2 points. And that's how they get their average, as opposed to the red line only using 1 point being an instantaneous. That's the distinction between the two. Does that make sense? Okay. All right, cool. That's. Oh, please, yeah.
So my name is Jared Castro, Gavin Castro.
Oh,
so
nice.
In regards to the limit, so hypothetically, if x was approaching 4, the function next, we would evaluate x at 4, if that's what it's asking.
Correct. So whatever it's asking you, whatever x is approaching, that's what you're going to approach it at. So eventually we're going to get to problems where I'm going to do something like this to you guys. I'm jumping the gun, but since you're asking the question, I'll do it. So if I had something like, okay, f of x is, I'll make it simple, 2x plus 5. It's probably too simple. Let me make it squared. Because if I made it just 2x plus 5, the slope is 2. That's uninteresting. That won't help. And I said, okay, this is going to be later on, but if I say find the limit as x goes to, I don't care, 3, right? In order to be able to do this problem, we're going to take the limit, right? But the way that we're going to take the limit here is we need to know the values. So when x is 3, what is y? Because that's going to give us our p. Does that make sense? So in this case, it would be, all right, x is 3, comma, what is that, 9, 18, 23? Did I do that right? Okay, so now from here, to do the limit, I'm going to take the limit as x approaches 3. And I'm going to go, all right, 2x squared plus 5 minus 23 all over x minus 3. And this may not end up being factorable, it may be something ugly, I don't know. But you would take the algebraic steps at that point to solve the problem. But that's how you would attack it. Does that help clarify it for you?
Yes.
Okay, cool. Okay, so that's 12.1. Is it okay if I go straight into 12.2? I mean 2.2? You guys okay with that?
Yes. Yes.
Okay, cool. So as you can see, I have all the notes already ready. Now what I'm going to do is, was it Gerardo? What?
Yes.
Okay, all right. Just making sure that I'm trying to get your names as I talk to you guys. This is actually addressing what you were just asking. So in 2.2, you can see I have a function, right? If you guys have your TI-83s or 84s, you may want to pull them out because they're going to be powerful tools, and I want to be able to show you guys how to use them to be a powerful aid in this class. If you don't have them today, no big deal, but I strongly recommend you guys have them. They'll be so beneficial. So in this problem, I'm giving you a function, and I'm basically saying, hey, let's find values as x gets close to 4. So what I'm trying to lead to is the limit, right? And so as I get close to 4, so using the function, if I plug in 3 into the function, I'm going to get 3 squared minus 2 times 3 minus 3. That's going to end up being 0, right? Do you guys concur? Oh, what did you say, Ray? Have a what?
You're saying to, if you don't have something, because the Zoom cut out as soon as you said the one word that was most important in the sentence. You said to have something by next class, or it would be of great help to you.
Oh, your calculator, a TI-83 or an 84. It's going to be a powerful tool to use, and I want to be able to show you guys how to use them to find all kinds of information that you've never used your calculator for.
Okay, awesome. Thank you.
Yeah. Okay, so, and if you notice something here too, which way am I approaching 4 on this side? From which side of... So I'm approaching, this side I'm approaching from the left. This is important. On this side, I'm approaching from the right. Okay? And I'll talk about what's happening there in just a second for a limit to exist. Because I made some assumptions in 2.1, but I want to address that here. So if I plug in 3.5, I'm going to get 2.25 as my number. Okay? If I plug in 3.9, I'm going to get 4.41. 3.99 is going to give me 4.9401. And then 3.999 is going to give me 4.99401. Well, where do you think this is going? What value do you think this is approaching?
5.
It looks like it's approaching 5, right? So it looks like this thing is approaching a y value of 5, right? But, and I'll talk about that, it looks like it's only coming from one side. In order for us to be able to say that this is a limit that's coming from both sides, I need to be able to show it, in order for it to be a limit, like I have up here, this piece, in order for it to be like that, I have to show that it approaches the same number coming from the left as it does coming from the right. Okay? So, when I plug in 5, I'm going to get 12. 4.5 is going to give me 8.25. That's going to give me 5.61, 5.061, and then this one's going to give me 5.06001. What's the other side look like it's approaching? Doesn't it look like it's also approaching 5? So from the left, it's approaching 5. From the right, it looks like it's approaching 5. And so I can say that the limit of x squared minus 2x minus 3, as it approaches 4, is going to be 5. Is that cool?
Yes, sir.
Yes.
So you're getting these numbers like kind of fast. Do you have like a way to like do it on your calculator, or do you have these like already like?
No.
down?
I already had them.
Okay.
Since I didn't. Well, I'm really good at mathematics. I'm doing this all off the top of my head. No. I already have it written down. But for you guys with your calculator, all you would do, and I'll demonstrate one for you. Since this is my function here, I'm going to plug in the values for 3.
Okay.
So I would go f of 3 is going to be 3 squared minus 2 times 3 minus 3, which would give me 9 minus 6 minus 3, which gives me my 0, which is the first number. Okay? But I had already done these beforehand. I didn't want us to do a bunch of calculations in class. But it's good practice for you guys. So since this thing is both approaching from the left and from the right the same number, I can say this, and this is, I can say with great confidence, the limit as x approaches 4 of x squared minus 2x minus 3 is 5. And I can check it. If I plug in 4 squared is 16, correct?
Yeah.
Minus 8 gives me 8. Subtracting 3 yields that 5. Right? And so we end up getting what the limit was by making a table. Now, what is this showing you guys? What it's showing you is if you don't know how to do the calculations algebraically, you can plug in values as you're getting super, super close to a number and find out what the solution is going to be. Okay? Which is big. Okay, let me do another example for you guys. So now look at this one. In this problem here, I'm going to do the limit of this thing. So as I'm doing the limit, I can see that the top portion of this thing is factorable. So I'm going to get the limit as x approaches -1 of x minus 3 and x plus 1 over x plus 1 which those are going to cancel, and so I'm going to get the limit as x approaches -1 of x minus 3, and what is that going to yield for me? Is that -4? Yeah. So that's the limit's value is that -4. Now, something important for you guys to notice. Could you guys tell me what the point is that I used? What was the point that I used for my value for my p in this case? Anybody? Do you guys need my help?
What do you mean with?
So you know how on the problems that I did before, I gave you a p-value that we were approaching, and it gave me a point. In this problem, there's a p-value. -1, 3. Very close, Jorge. Very close. It is -1.
It's not -3.
No, and it's not -1, 4. Very close. So here's something cool. It is -1, but what's the function?
Oh, 3. That's much.
You guys ready for this? It's 0. I'm going to help you out. I'm going to help you out so you guys can see it. It's this function. It's this function. But if I plug in -1, what do I get? -1 squared is 1. -2 times -1? 1 plus 2?
3.
Minus 3?
Oh, 0.
Now, what I did is I made it abstract, right? This is my p-value, and this is one of the things you want to get to the point where you guys can see so you can understand what's happening in terms of the curve. If I'm approaching p, I need to figure out what the function is, right? If I want to be able to do more with it. So I changed my what number I was approaching to see if you guys could see what our p-value is. Now, there are times you may not be able to find it. So, like let's say that this would have been done a step earlier where this was x minus 2 was the function, and they subtracted 1 or some other number, you might not be able to find it. But in this case, I set it up so that you could. So what you end up doing is plugging in that -1 into the function, if you can see what the function is. Does that make sense?
Yeah.
Okay. All right. And now I'm going to show you. I did it algebraically. Now you guys try to do it. This side up top, these guys here are approaching from the what? They're approaching from the left, right? Because -1 is further to the left, and these are approaching from the right. As I do this, I have the values. I won't make you guys do it because I'm sure you don't have your calculators with you. This one's going to be -4.01. This is a -4.001. This one's a -3.99. And this is a -3.999. Now, we can see the middle two terms, we're approaching -1, right? The on this side, we're approaching -1 right here, right? Between these two guys. What are we approaching here?
-4.
We're approaching -4. Now, here we definitely know it's -4. Here we're still kind of making a guess, right? So since we don't totally know here, one thing that you can do, and it's a technique that you can do, you can add these two and divide by 2. You can end up taking the average, and guess what the average is?
-4.
-4. So that's a technique that you're going to do. Correct. Add the middle 2 and divide by 2. This is going to give us that -4. In the homework, there'll be a problem where you're going to have to, or to get the best answer, you're going to have to do this technique of taking an average. So that's why I wanted to demonstrate it to you guys. Okay?
Professor?
Yes.
What does it exactly mean when it says like left and right?
Okay, so cool. It's the way I'm approaching it. So with limits, right, if I took a number line, if this is -1, and this is -1.001, this is -1.01, here is a -0.999, here is -0.99, over here 0, right? Well, our goal is to get here, right?
Yeah.
So as I'm coming from this value to this value, right? So as I'm coming from here to here, the goal is to get to this yellow, right? Which way am I coming to the yellow? From which direction?
You're coming from the left.
From the left. So that means I'm approaching it from the left. On this side, I'm approaching it from the
Right.
From the right. Now, the only way that a limit exists when it just says the limit as x approaches a specific number is if it comes to the same value from both sides. Okay? If it doesn't come to the same value from both sides, what we end up having is a one-sided limit. Okay? We end up with a one-sided limit. All right, so let me show you guys that. But it's good that you asked that question because it showed you the approach. And the approach, just so you understand, coming from the left or coming from the right, if I say as x is approaching a number, that's going to be left and right. If I say as y is approaching a number, now we're talking about top and bottom. Does that make sense?
Yeah.
Okay. because it just depends on the variable that I'm using. Okay. Okay, one-sided limits. This is important. So if I'm going to approach from the left, okay, the notation for approaching from the left is going to be the limit as x approaches some number a, and I put this notation right there. See that little negative? The negatives are on the left, or coming from the smaller side is on the left. I put that notation of f of x, and then it equals my limit L. Okay? If I'm going to come from the right, I'm going to have the limit as x approaches a, and how I know I'm coming from the right, I'm coming from the positive side of f of x, and this is going to be equal to L. And these L's aren't necessarily the same. Okay? All the L represents there, all it means is limit. Okay? This is the goal. The limit as x approaches a of some function f of x, it's equal to L. The only way it's equal to L is this. Have you guys ever seen this before? Has the teacher shown you that before? So IFF means if and only if. Okay? So the only way this can happen is if and only if the limit as x approaches a from the left of f of x is equal to L, and the limit as x approaches a from the right of f of x is equal to L. So the only way that we can have this thing is if the two one-sided limits equal the same value. We okay?
Yes.
I mean, I'll definitely do an example so you guys can see it, but it's the abstract first, right? Okay, so let me do an example. You guys have this written down. Am I going too fast for anybody? You guys feel okay? It's a decent pace? Okay. Yeah, I'm just kind of feeding off of what you guys are asking and saying to me. But you also have the ability to rewatch it later, so there you go. All right. One thing I did want to tell you too is I'll post this video up for you, but my YouTube channel has everything from chapter 3 on, so you can watch my lectures from last semester and compare them to my lectures that I do with you guys, because maybe they'll ask questions that I didn't ask. If you guys are interested at all in watching them, I have them up so you guys can watch those too. All right, let me do this right here for you. In this problem, I'm going to call this x. I'm going to call this the y-axis. And I'm trying to find out what the limit is for this thing as it approaches 1. Now, one of the things I see is it's undefined if I plug in 1. So that gives me it's going to give me a vertical asymptote at 1. And I also know that this has, it also has a horizontal asymptote at 0. And then my function's going to look like this. And all I'm trying to do here is demonstrate this for you guys pictorially so you guys can see another way to do this problem. Okay? Oh, no problem, Oscar. No problem at all. Okay, this is being recorded too, so you'll be able to rewatch it. It's no big deal. Okay, so now in this problem, what we're trying to do is we're trying to find the limit as I am approaching 1, right? So I'm going to do the one-sided limit coming from the right. So the limit as x goes to 1 from the right of this function is equal to what? So what's happening here is as I'm coming this way along the function, what is my y value as I get closer and closer to 1? What do you guys think it is? Correct. It's going to be positive infinity, right? Because we can see as I'm coming this way to it, the function is just going to explode to infinity, right? So from the right, I'm getting a positive infinity. Okay, so from the left, as x approaches 1 from the left of 1 over x minus 1, I'm coming this way, I'm approaching 1. What is my y value there?
Negative infinity.
It's going to be negative infinity, right? Rico? So yeah, I mean, it's. I think it'd be useful for you guys to be able to print out my notes. I'll put those up for you guys over this weekend. I'll put all of them. I'll put every from 2.1 to 6.5. I'll have all of the notes up for you guys, so you guys can print them out. It just will save you time from some of the typed out stuff that I have, so you don't have to like cram your hand up printing it out. Okay. Now, from the right, from the left, are these equal? The answer is
Yes.
no. One of them is positive infinity, one's negative infinity. That is not the same number. And since it's no, the limit of our problem is dne. And what dne means is does not exist. Okay? So what I'm trying to demonstrate here is this definition that I just had up here. This only happens if these two guys have the exact same limit value. If they don't have the same limit value, it will not work. Cool?
Cool.
Okay. Do you want me to do one where it does, so you guys can see?
Yes.
Well, we did one actually in the previous notes. We did one where it worked, where we had -4. Remember I showed it from the right and from the left, and it gave the same -4 value? Or, I'm sorry, the 5, it gave the same 5 value? That was showing that from the left and from the right was the same, and so the limit of that function counted. It wasn't one-sided. Okay? Here, I'll go back and show you real quick. So, was it in this one? Oh, it was in 2.2. So like right here, that's an example of I'm coming from the left, I'm coming from the right, we got the same numbers. Over here, coming from the left, coming from the right, we had the same 5, and so see how I wrote it there without a right or left symbol? This is showing that coming from both sides, the limit did exist. Does that make sense? Okay, cool. All right. Starting to build. So this definition is a cool one. So in order to have a vertical line, and we know that the vertical line is x equal to any number, right? That gives us, in order to have a vertical line that is an asymptote, a vertical asymptote, what ends up happening is one of 6 possibilities must come about and be true. Okay? So, for that to happen, here are these are the 6 possibilities. 1, the limit as x approaches a of f of x is equal to positive infinity. So if the limit equals infinity, we end up with a vertical asymptote. Okay? If it's a limit from approaching from both sides, we have a vertical asymptote. If the limit as x approaches a from the left of f of x is equal to positive infinity, we still have a vertical asymptote. If the limit as x approaches a from the right of f of x is equal to positive infinity, we have a vertical asymptote. If it's equal to negative infinity as it comes from both sides, that's a vertical. And then the 2 one-sideds. Coming from the left or coming from the right. So what it's telling us here is if we have a limit that ends up equaling either positive or negative infinity, the number that it's approaching is where we have our vertical asymptote. Okay? So in this example, the number is a. So wherever a is would be the vertical asymptote. Okay? Sure, go ahead.
Well, I'm Jorge.
Yeah.
Can you scroll up to our previous example? Wouldn't it also just be a vertical asymptote if your denominator were to equal 0 if you directly substitute?
Wonderful, you're right. That's what you learned in Algebra 1. Right? But this is calculus.
I actually took calc in high school.
Yeah.
I'm taking it again.
Yeah. So wonderful. But really the method that you're talking about is a Algebra 1 method. And this is a calculus class. And so to demonstrate vertical asymptotes, I'm going to require that you demonstrate the limits go to positive or negative infinity. So while you're right, the reason that is because the limits take off to infinities. The way that you're explained it in Algebra 1, where the denominator is equal to 0, that's undefined. We don't know what happens there. And so it's not till you get to higher levels of mathematics that you understand what those things mean. So eventually in this class, I'm going to show you stuff where things that you've taken for granted, I'm going to give you reasons for why they are what they are. And since you've taken calc before, you should understand why being undefined doesn't make this a vertical asymptote. the reason that that ends up working out is because of the limits having the function take off to infinity. It doesn't cross the vertical asymptote because it takes off going straight up or down. Undefined just tells us we don't know what's happening there. Does that make sense?
Yeah.
Okay. It's a good question, and it's true. You can check it that way. In my class, if we would have had a in-person class, that would have been one of my test questions, where you would have had to demonstrate using calculus the vertical asymptote. And in fact, we probably will end up doing it anyways in chapter 4. But just please know these 6 conditions, okay? All right, so just to show you, if I go the limit as x approaches 2 from the left of a function like 4 over x minus 2, this is actually pretty cool, and this, Jorge, may help you. Does this ever get to the number over 0? Because this is important for you guys to understand. The example that I have here doesn't get to the number over 0. It actually gets to a number over something super, super, super tiny. Because, like I said to you guys early on in the class, you get to the neighborhood, but you never get to the house. The way I talk about limits to my students in the past is, it's like a guy who's in love with a girl, and he buys her flowers, and he knows the neighborhood she lives in, but he can never give her the flowers because he doesn't know which is her specific home. So with limits, you're never getting to the girl's house. You're just getting close. So in this example, I'm going to have 4 over some number that is super, super tiny. So I know that this is going to end up being negative infinity, but I'm going to show you why it's negative infinity right now. Okay? The reason it's negative infinity is if I use a number like 4 over, and I'm getting really, really, really close to 2, but I'm getting close to 2 coming from the left, so I could have 1.999999 minus 2, right? But what does that end up being? Isn't that 4 over 0.000001? Right? This isn't that number over 0 thing, because we never get there. Because if we plugged in 2, we'd have 4 over 2 minus 2, which is undefined. We don't know what that is. What this ends up being is 1, 2, 3, 4, 5, 6. I think I did the math right. You guys may want to check with a calculator. I may be off by a decimal. But
Negative.
What's that? Oh, and it's negative. Yes. Thank you. Because this guy's negative. You can see it becomes this astronomically large number. Right? And so what do we see that this thing is tending towards? It's tending towards a huge, huge negative number. Well, how close can I get to negative 2? Well, how many decimals can I write? Right? 1.99999 forever gives me these astronomically big, big, big numbers. So we say, where's it going? It's tending towards negative infinity. This right here would be enough for me to say we have a vertical asymptote at 2. Because this is demonstrating number 5. Right? So from here I can say, therefore, we have a vertical asymptote at x equals 2. We okay with that? And one of the things too is we could even show it the other way. So if I had said the limit as x approaches 2 from the right, I know that this is positive infinity. And the reason I know it's positive infinity is I can see this. I'll do it. I'll explain it to you guys in a quick way, and then I'll do it mathematically so you guys can see it. If I'm coming from the right, isn't this like 2.1? Right? So I'm getting 4 over 0.1, which is 40. Right? And so I already know that means that thing's going to positive infinity. It's exploding up. Is that clear? So if you don't see it, you can always do it this way. And the biggest problem that people end up making is they don't understand right and left. So it's imperative that you guys understand which way you're coming from. So in this example, I'm coming from the right. So I'm going to go 4 over 2. And again, 0.001 minus 2. That's going to give me 4 over 0.001. And we can see that's going to be 1, 2, 3. So I got to go 1, 2, 3. That's 4,000. That thing's exploding to positive infinity. And so I know that this thing is in fact going to be positive infinity. Now, how many do I need to demonstrate in order to be able to say I have a vertical asymptote? That's easy. I only need to demonstrate one of the 6. Okay? Any one of the 6 that I can show that goes to positive or negative infinity, I have a vertical asymptote at that specific point. Okay? Biggest thing about today that I can stress to you guys is limits get you to the neighborhood. They don't get you to the specific number. So you don't ever have to worry about being undefined because you're never going to get to the specific number that it's telling you to get to. You're just going to get what we say infinitesimally close. Okay? Do you guys have any questions for me?
I think I'm doing good so far.
Okay, cool. I think our class, what time does our class end? I think it's 12:30, right?
I think it's like 12:30, 12:35-ish.
Yeah, 12:35.
Yeah, right.
That's all I've got for today, though. And I don't want to move on and overwhelm you guys. Do me a favor. Hop on. It's 12:35. But typically I give a 15-minute break, so that would make it like 12:20. But the one thing that I want you guys to be able to do right now is let's hop off for today and have you guys set up your web assigns so you guys are ready for doing your homework. Here, I'm going to stop the recording so I don't need this on the recording.